This broadcast will be focusing on Chapter 4. What we have is a fairly detailed chapter in some regards and a fairly general chapter in others. So some of this content we will go over quite rapidly. Other content we will not go over as fast. We'll slow down just a little bit. Further, we will have a follow-up content slide in the next session that you'll have available electronically to reinforce some of the terms and some of the content that has not been well received in the past. So we do have a little bit of technicality in this chapter. So let's get right into the details of it. It starts off nice and general, and what we're getting into is the idea of a flowing system of the hydrologic cycle. And the terms that we should know are our traditional terms. You see evaporation, precipitation, but do work on the understanding of infiltration here and transpiration. Furthermore, if we take transpiration, which is a biological process centered in plants, and we connect evaporation and transpiration to evapotranspiration, then what we're into is a system that's somewhat likened to that of a plant sweating and then evaporating that moisture. So that's kind of a crude example of that process. The other thing we need to pay particular attention to is the discrepancy between evaporation and volume. We have 320,000 cubic kilometers that are evaporated. However, we have 284,000 that are returned back to the ocean. So there is a discrepancy, meaning that the idea of the water cycle isn't fully balanced. And that's something that we need to have a more thorough understanding of at this level. Moving forward, we have water. These are 5 unique states of water, not states in regards to the solid, liquid, gas, but states is in regards to properties. So when we look at all of these, most are fairly well received. The one I would draw your greatest attention to is ice. The solid state is less dense than liquid. You've noticed this before, and we take it for granted, but that's weird. For example, when we have a solid and we begin to melt that solid, most of the time, the liquid part of it, is less dense than the solid. Therefore, the solid part typically would sink. And we would see that in a lot of applications, but not with ice. And the reason being is because of the expansive quality whenever ice moves into a rigid form or a solid state. So that's something that's quite unique. And you've seen water in a solid form, ice, float in a liquid beverage for a great deal of your life. And you've seen that on bodies of water. There's a lot of examples that we see. Icebergs, classic example. Very massive chunks floating whenever we can question how that's possible. And the other thing we need to make sure we grab well is the high heat capacity. This is the specific heat that we've talked about before, and we've got to go into a greater analysis of latent heat within this chapter. You're going to do great. We just need to talk about a little bit more formal numbers and make sure that information flows with a little higher understanding there. The ability for water to form hydrogen bonds is something that's hopefully well understood to you. We do have 105 degrees of separation between the hydrogens, and that makes a very unique property whenever we have a crystal lattice in form. This is focusing on the concept of water moving from one state to the other, and the ideas of water melting and then moving from a solid to a liquid to a gas is fairly common. However, we do see an uncommon term here with sublimation because it skips the liquid state. So when solid flows to a gas, we have to put energy into that solid, meaning the energy has to be taken from the atmosphere. So what we would have there is a cooling process in the atmosphere. When we move the other way and we have gas moving directly to a solid, since gas is more energetic, it's got to give that energy off to move into a more settled form like that of ice. Therefore, it's going to give energy off, meaning that we have a depositional feature in the atmosphere that's going to return heat to the atmosphere, making this a warming process. So when we see these areas in blue, like condensation and like freezing, would that be considered a warming process to the atmosphere or a cooling process? Warming. Why? Because we're moving from a higher energy to a lower energy form. If we turn that comment around and we move the flow of energy in the other direction, therefore we have to have energy into the ice. We have to have energy into the liquid, flowing into this liquid for it to move to a vapor state. And because of that, then the atmosphere would be cooled. Latent heat, return to this. The difference in this chapter is our calorie component. So what we have here is ice requiring 80 calories to jump, And that's where we have those types of things whenever we have melting. And by jumping, I mean for it to go to a higher state. Freezing, we have a release of 80 calories, and that is returned to the atmosphere, making that a warming process. One little quirk here is when we say freezing, informal, what we're talking about is the latent heat of fusion. So sometimes that throws us off in this chapter, but the latent heat of fusion is talking about the concept of freezing within chapter 4. These are all processes we should understand. You did well with this in our last chapter. However, we did not focus on calorie counting. So that's one of the things we're going to do here, a little bit numerical. We'll use calculators to kind of get an idea of how much energy is being gained or lost into the atmosphere. So these are things that are either warming processes or cooling processes. So because of that, we see evaporation here being stated as a cooling process. That's why we can have evaporative coolers in areas of Nevada. Sometimes you can see professional teams having large misting fans, and that's the process, that's the science behind that. So when we look at the other side of things, condensation is a warming of the atmosphere. So these types of things are a little bit different when we consider those two perspectives. Sublimation and deposition, spend a little time with these. Great example here with frost accumulation in a freezer. A lot of times the more modern freezers today are frost-free, so you may not see a great buildup in that freezer unless you have an old one somewhere tucked away in a garage or basement somewhere. But you may not have that good association. You might be a little bit more familiar with trying to scrape frost off of some form of a windshield, or you see it on a pane of glass. That might be a little bit more correct. Instead of the frost on a freezer. So the difference there is we might have some frozen dew associated with that instead of just frost. Take kind of a peculiar situation there. And then sublimation there. Disappearing ice cubes in a freezer, that's a great example. You can certainly see those, and that's why we talked about in class we have those ice cubes in the back of the tray or the ice container. They get smaller and smaller, but we don't have water dripping from the freezer. But we do have evaporation. It's just happening at a much slower pace. Moving on, this is where we get into a little bit technical detail. We will have another slideshow, another lecture presentation over these terms that will show things from a little different perspective. But for right now, what I would really encourage you to do is spend some time reading the difference between these. I'm not going to spend a great deal of time going over each one of these in detail. That'll be the intention of the next slide presentation that you can look at in about a week's time. But please spend some time with just understanding the differences between those. We will open up this session in class working with a lab and relative humidity. Hopefully you had a course in the past where you calculated relative humidity. It's a nice ratio process. It works very well. There's some hands-on component. We can do this in several different methods. We will try to work with relative humidity and dew point 2 times in a lab sense to reinforce that. So those are things that we'll see. Now, saturation vapor pressure is something that relates to partial pressure. If you can understand the partial pressure that we dealt with, like Dalton's laws in the past, then you've got what you need to understand saturation vapor pressure. The difference is it's just vapor. So what is vapor? It's a compound. You know what the compound is. It's H2O. So instead of answering questions about what is the partial pressure of nitrogen, whenever we have 1,000 millibars of total atmospheric pressure, now we're just concentrating on what? Because it's vapor pressure, it's just water. So water ranges from 0 to 4%, and we would just need to apply that understanding at a particular geography and try to figure out what the vapor pressure is. Specific humidity, this is where we have a mass of water vapor to the total mass of the air. This sometimes creates a little bit of confusion, and I think when we get into our next discussion series, it'll make a little bit more sense. But do spend some time trying to commit these to memory, looking at some diagrams, get a basis of understanding there, a platform, if you will, to stand on, and then in our next session, I think you'll have a greater degree of understanding as far as clarity of thought. Absolute humidity, mixing ratio, and vapor pressure all fall into the same thing. So here's the challenge, gang. You have 7 concepts here, 2 of which are hopefully pretty well understood to most of you, depending on what courses you've had in the past. However, all of you will probably be challenged with at least 5 of these. These get confused. That's why we're going to have 2 lecture presentations over these. We have absolute humidity, which is just taking mass of water to the volume of air, but we're talking about the idea of a volume change that goes into play there. Sometimes that can be a bit misleading to some. Mixing ratio is what we're talking about in dry air only, and we'll look at a diagram in our next discussion there. And then vapor pressure, this is the total part that we're talked about there in regards to saturation vapor pressure. Very similar, except one is talking about a partial pressure because the air is not saturated. And then when we say saturation vapor pressure, we're talking about a relative humidity or a very, very saturated environment. So spend some time on these. This is your big stumbling point early in the chapter. We will do some lab work on this, and we will hopefully reinforce it through there. But a lot of this is just going to be put on your shoulders to kind of dig into. So those traditional flashcards have worked pretty well in the past with these, and you will have a reinforcement set of questions that'll give you scenarios to try to make a good specific connection to. So dig into this content. Here's a couple slides that'll help. And again, we'll hit some of this before. This is the vapor pressure. Normally not a big deal, but do notice these pressure gauges at the top. These pressure gauges will change as we have greater evaporation. We put more water molecules in there, and we're going to drive that pressure up. That should make sense because when we have the same amount of space and we start to pack that full of more water through greater evaporation, then we're going to drive pressures up. So how do we do that? Well, we either heat the water or we create evaporation from a process of some form of a change there. And we could do things to the partial of the air, or we could like volume, or we could more traditionally do things to the temperature of the air. Saturation, this is no technical concept. You've got this. This is the idea of a equilibrium being met. Typically, we think of a sponge, or every drop in equals every drop out. What causes this to change, or what changes does saturation cause to the atmosphere? An increase in temperature. We have a higher vapor pressure whenever we have humid air because we have an environment similar to these pressure gauges. So when we have a point X here, a very humid environment, we're going to have more vapor pressure. Why? Because we have more vapor. So when we see those things, we have correlations that do connect very well to our discussions in the past about atmospheric pressure. Relative humidity, this is the #1 used depiction of moisture in the atmosphere. Unfortunately, it's the one that society does not understand that well. So here's the challenge. It is the ratio of the air's actual water vapor content and amount of water vapor for saturation at a certain temperature. It's not the amount of moisture that's in the air. It's a comparison. It's the actual vapor and water vapor required for saturation at a certain temperature. We do use this quite a bit. It's a percentage form, and we talk about it a lot in regards to severe weather because of its latent heat capacity, especially in the afternoons, and we can give that energy off, driving those intensities of storms up considerably. How we change relative humidity here. We have a saturation environment that can be met at 100% if water vapor is added. We are going to drive that up, ultimately tapping out at 100%. If we remove water vapor, humidity is going to go down, and a decrease in temperature equals an increase in relative humidity. Why is that? Well, think of condensation. So it's similar to that process in regards to what you see with the deposition or the condensation of water within a contained environment. It's a very similar process. Here's a few classic examples. These are fairly common depictions of this situation. Notice first across the top that our temperature does not change in this sample. We're at 25 degrees. However, do also notice that we have a change in grams of water vapor. We have 5, 10, and then finally 20. What we do change is relative humidity. We have 25%. Our kilograms of air doesn't change. It's all the same, each one. And then we have 50%, and then we have 100%. And what we changed here is we changed the idea of our relative humidity. So we have 25% relative humidity when we have 5 grams of water vapor. When we increase, allow evaporation to take place, and we increase that suspended water vapor, we're going to increase the amount of humidity in the air. Okay, so think of us getting like more tropical, more mid-latitude versus in a polar location here, very dry air. And then if we continue that evaporation and we continue that over time, then what we're getting into is a relative humidity that would be similar to that over the equatorial region. Very tropical, very steamy, very balmy, not unlike some of these Ohio Valley summers that we have. Very, very sweltering as far as that humidity. Natural changes. These things affect relative humidity. We have temperature changes. Advection, remember, is the moving of air horizontally. What we have is a convective flow, which is wind moving things across. Temperature changes are also occurring because of convective processes in the atmosphere as well. Don't forget about your radiation convection. So we do have to make connections to those. So those are natural changes that take place. Sometimes when we talk about these concepts, we do have to bring in the idea of dew point. This is intuitive. The dew point is just simply the point where we're going to form, you got it, dew. So when we have this condensation and we have a temperature where condensation is being met, we're going to refer to that as dew point. And that's one of the labs that we'll reinforce pretty quickly in class. And normally you guys do outstanding with this. So here's what we see is thresholds within this. When we're into this threshold, we have an environment that we have very little snowfall being produced, mainly because of why. If we have this dew point at this temperature, are we going to have moisture that's suspended in mass quantity or very little quantity? If we don't have a very high dew point temperature, we're not going to have very much moisture suspended. However, if we drive this up as we move down here, look at what happens to our amount of water vapor connection. Rainy tropics, humid by most people, is 65 degrees Fahrenheit. We're going to be probably delaying most outdoor activities in the fall or early spring during a warm spell if we're close to that 70-degree threshold. That's going to make it pretty hard on our bodies, especially if we're wearing equipment. Hygrometers. You're going to work with a hygrometer in class if you haven't already. These are things that measure the moisture content of the air. We talked about one early on. That was a hair hygrometer. We're not going to work with a hair hygrometer, but we're going to work with one that's a sling psychrometer, and it's a form of a hygrometer. So hopefully you've heard of that before. If we have time in our lab processes, we will also work on a dew point style hygrometer, which is a very classic, simple example. A psychrometer is like that of a hygrometer, and when we have a sling style psychrometer, what we're looking at is basically two thermometers going back to back. One's a wet bulb and one's a dry, and we're going to determine the wet bulb by a cloth substance around the bulb that's going to retain moisture, and that allows us to calibrate how much moisture is being lost. That's going to be referred to as a depression. So whenever we have moisture being lost from a wet bulb apparatus and that temperature drops, we're going to say that depresses the temperature. So what we get into and what we will calculate or what we will find on a chart in class called a psychrometric chart is the wet bulb depression. So sounds a little bit complicated. Hopefully you've worked with this before, and maybe your memory will be jogged when we work on it in class. Adiabatic process. This is one that I know you've worked on before. If you've had the Earth Space One course or something along the line of a climate-based course, this is where we have no heat is transferred, but we have a temperature change. We did talk about this in chapter 1. We dealt with lapse rates, and that is what adiabatic temperature change deals with. So when we talk about a temperature change without the addition or removal of heat, what we're doing is either expanding air or contracting air. When we expand air, it's cooling. When we contract air, it's warming. So what causes this to happen? Well, we either have unusual pressure centers or, most dramatically, mountain ranges. And that's where we get into an orographic process that we will practice with in class. So within this chapter, we will practice with orographic adiabatic process, and it'll make sense. But we will take our lapse rates and divide it up into two categories and compare it to the environmental lapse rate at 6.5 degree per kilometer that we talked about before. So when we look at these types of processes, here's our two lapse rates that we need to deal with. We have a dry adiabatic rate, and that is a value of 10 degrees Celsius per 1,000 meters. Well, that's a disparity whenever we looked at our environmental lapse rate. When we were looking at our environmental lapse rate about 6.5 degree per kilometer or 1,000 meters, it was quite different. When we reach a condensation level or a lifting condensation level, what do you think happens? Well, condensation level must be that condensation forms. In the atmosphere, what would be building in the region called the condensation level? Those are the processes in the sky that we call clouds. So when air rises and cools to a point called the lifting condensation level, or LCL, we're going to have a cloud form. And that is because we've hit the dew point. And that's one of the things that we will drive forward, because we will be able to use adiabatic temperature change to predict and determine cloud base altitude. And those would be things that we can focus on. Now, what happens when we hit the cloud base there? Now we're going to move into a wet adiabatic rate. Notice a reduced amount of the wet adiabatic rate. We're only at 5 degrees Celsius per 1 kilometer or 1,000 meters. So we're cooling at less efficient standards. We're about 50% as efficient. Why? Because of latent heat. All that water is giving off energy back to the atmosphere. Therefore, we're not able to cool down. Not unlike you on a hot, humid summer day. You're not able to cool down nearly as well either with all that bulky humidity around you. And so what you are experiencing there is the effect of something similar to the wet adiabatic rate. Again, we will practice with this in a lab and calculation form in class. Here's the adiabatic temperature changes in a graphical sense. I think you have something similar to this in the version of the textbook that you're working with, but do pay the most close attention to this slide, the one on the right. And the condensation level here is most of the time around 3 kilometers, 3,000 meters. And that's the one we're going to talk the most about in class. In reality, that changes a little bit. Depends on where we're at, but we're going to average that out and have a nice discussion point so that you have something static to work with and get used to this, this information. Orographic, we mentioned that before. This is where we hit that mountain range. When we have a leeward side and a windward side, we have two sides of a mountain. We definitely need to know the difference there. There is some intuition that goes into it. Wind hits the windward side. So that's going to be where the wettest places are, because that's the air lifting, and we're going to lift it and allow condensation to occur, and we're going to have clouds that generate moisture. Leeward side, this is the side of the mountain that the wind has gone up and over and that is now sinking. And so since the moisture has been lost out on this side of the mountain, what type of biome do we have? Is it a temperate forest or is it a desert? Hopefully you know that it's a desert region. Here's a nice diagrammatic example. So this would be, the X would be a leeward side or a windward side. Definitely leeward side of the mountain. So we have the windward side is creating an uplift here, and then we're getting cloud formation as we see depicted. And what we have here is a temperate-like rich forest, entirely different soil profiles versus a soil profile that is extremely different on the other side. So although these latitudes might be almost identical, you have entirely different biomes, entirely different soil profiles. And one could be podocal, one could be podalpha, and it just has an entirely different matrix because of the lack of or presence of atmospheric moisture. Frontal wedging also lifts air, and this causes us to have an air temperature change as well. So what we're talking about here is one air mass with more dense molecules, placement of molecules, cold air, rise or ridging into a warm air, causing the warmer air, which is more buoyant, to rise up. And that's causing clouds to form. And you've noticed this before, but we're going to call this, and we're going to discuss it from this point forward, as frontal wedging. So when we have two fronts being two parcels of air that are different temperatures in the atmosphere, and they drive into one another, that's going to be a process that lifts the air. So far, this is two processes that lifts air in our atmosphere, and we're going to build on these. You have one, which is the mountain range, and we called that what? Started with an O, orographic. And then this is our second one, which is our frontal wedging. The third one that we will recognize is convergence. So the classic example here is being Florida, and you can see in the outline in the picture below the peninsula of Florida. And as air flows inland from the east and west, we get a temperature difference over land. Remember our specific heat difference, and that's where we're going to get converging air over this. So this is the third process that causes air to lift in the atmosphere. We have orographic process, we have frontal wedging, and now we have convergence. Localized convective lifting are huge bubbles in the atmosphere that take place because of solar heating. This is why that solar sun angle is so important, why we talked about it earlier in the course. So what happens around midday, we have a thermal that rises, and what flows on those thermals up here are birds. Birds will just soar around, and you've seen those larger birds just almost floating on an invisible current of air. We can't see it, but we know it's there. They don't do that in the morning, they do that in the afternoon. The reason why is the ground has to be warm. And as time goes by, we lift this up to the lifting condensation level. Can you recall what altitude value that it was? It's about 3 kilometers up in the atmosphere. And as that is there, then we see this cloud base, this distinct cloud base forms. Well, what do you think happens if the ground is unusually warm and we've got an unusual amount of moisture to work with? Does the height of this cloud get higher or lower? It's definitely going to get higher. And that's where we get into some of our more interesting and severe weather feedback that we'll talk a little bit later about. Do notice the flow of time from the left to the right on the chart. This gives you a nice depiction of sequences within this process. So overall, what we have there are mechanisms that have lifted the air. And anytime air is lifting, it's going to be called unstable. And that's what we've looked at there. There are several things there that we discussed that are unstable mechanisms to that process of air. It's lifting that air. It's either a mountain range causing it to lift up, and that can aggravate the air, whether it be convective lifting, frontal wedging, convergence. Those types of things are going to aggravate air that is unstable, and it's going to cause it to potentially lift more aggressively, creating an outbreak of thunderstorms. Stable air resists vertical motion. So stable air is going to be air that doesn't want to change place. Stable air is something that wants to stay where it's at. It doesn't want to move. And so it typically is going to return back to its point of origin. And our environmental lapse rate that we will work with is something that gives us a calibration point. We worked with that earlier in the course as about a 6.5 degrees per kilometer. And that'll be something that we continue to use as a baseline. So what we will work on in this chapter numerically is how to determine whether an air mass is stable or unstable compared to the environmental lapse rate based on a sounding. Remember that rad synode, that sounding, that weather balloon? That'll be something we bring into this point in the course. So here's the depiction. Absolute stability. Here's our environmental lapse rate. Notice how we have temperatures down here at the bottom. And we have very stable air whenever we have the temperatures that are cooler than the environmental lapse rate. Meaning, as we ascend, as this goes up to higher points in the atmosphere, no matter where we ascend to, this parcel of air is always going to be cooler than the environmental lapse rate. And as long as it's cooler than the environmental lapse rate, as long as it's less than the environmental lapse rate, it's not going to lift. It can't. And so that's what we get in here. So when we see our rising air and we get down here to a temperature, as long as this temperature that it reduces to is cooler than the air that's around it, then it's going to be considered a stable air mass. Meaning that the only way that it's going to lift is if it's forced upward by some type of a wedging mechanism, which in this example is an advancing cold front, because cold fronts are going to advance at the bottom of the atmosphere first and wedge that, slide that up. And then we get that process that takes place there. But this would be a very stable atmosphere. Not much to worry about from the outbreak of storms. Here is absolutely unstable. Notice what happens to our line. So here's our purple line. That's our environmental lapse rate. Our environmental lapse rate is our baseline there. And we have things that are warmer than that, meaning that the air will be doing what? No matter where it's at in the atmosphere. No matter where we talk about in the atmosphere, this air is going to continue to rise. And because it's rising on its own, it's going to be considered an unstable or instable air mass. So this is unstable air. Unstable air happens to be warmer. The temperatures here are going to be warmer than the air around it, meaning that it's going to continue to rise. And so when we see these types of things, these give us an idea of why air rises, why is it buoyant compared to other air masses where it's not. Why is this a greater environmental threat to the outbreak of thunderstorms? Because it can rise on its own. When we were in this area, we couldn't lift this air unless if we had some lifting mechanism. These guys are free agents. Unstable air is able to gain enough energy and it's going to rise on its own. And then as it begins to rise, if it has enough energy within that system, as the atmosphere cools through the afternoon, it could produce a pretty significant feedback. Conditional instability. This is one where things are good for an earlier portion of the day, usually in the morning or early afternoon. Then we have a crossover and the temperature begins to get warm enough at certain altitude where it's going to be able to take off on its own. Normally what we have is some trigger in here, maybe a little cold front pushing this through. So in this part of the atmosphere down here, what we have is something that is a stable environment. This morning has been great. And then we have a little bit of cold air come in that forms a uplift. And that uplift then drives that temperature, which is a little bit warmer, up. And then all of a sudden it's in a cooler area of the atmosphere and it can take off and it explodes upward. And that produces a massive outbreak of thunderstorms. And that sometimes is why we see this thunderstorm event being in our afternoon hours, because of these types of feedbacks. So how do we change the stability? Well, we definitely need warming. Remember all those depictions of sun and those sun angles we talked about? We need some heating of an air mass below. We need some general upward motion of air, something that's going to be caused by those lifting mechanisms, whether it be a mountain, orographic lifting, a frontal wedging, and then convergence, something to give it a little nudge upward. Or we could have some radiational cooling from cloud tops. These are things that change our stability. So maybe the clouds rolled in and took a would-be unstable air mass and kept it in a stable category. We can have enhancement of stability from this, where we have radiational cooling or cooling of an air mass from below as it goes over a cold surface. Think like snow or water, especially if we're in the spring. And general subsidence, that's sinking within a column of air. Temperature changes. When air is cooled from below, it's going to be more stable. In winter, air is rendered sufficiently unstable when cold air will pass over a warm, wet surface. And that can produce a lake effect snow. And these guys can be amazing outputs of snow. We're talking about outputs of snow that in record-breaking format can be 6-7 feet of snow, sometimes 11 feet of snow, where we get to the point where we have to evacuate structure because we're not absolutely certain the roofs are going to hold that snow load. So those are things that we've seen in our local national news. These are areas like Buffalo, New York, regions that are on which side of the Great Lakes, west or east? If we have prevailing westerlies, like most of you understand, we've got to be on the east side of those. Subsidence in general is a downward airflow. Sinking air is what was mentioned before. Usually we're not talking about surface air, it's just from aloft, and that's something that's going to drive a change in the atmosphere. Normally when that takes place, we're having a little bit of a warming compressional effect, and we got beautiful, clear, cloudless skies. That's going to do it for chapter 4. This chapter is going to require a little bit more time, gang. I would really recommend digging in here, probably unlike what you've had to do before. And what we're going to have to get to there is a different view altogether. So this is going to be followed up by a view that is going to be just a focus, by a slide presentation that's going to be just a focus on the types of humidities. So do make sure that you spend more time with chapter 4. You have several different technical aspects. Probably the most technical is going to be that deals with the idea of humidities. That's what's been most confusing in the past, but we can't forget about the concepts of stable and unstable air. Some of you will do very well with that. Others will have a difficult time grabbing onto that. So those are the two areas that in the past we have had the most grief with, having a point of clairvoyancy of learning that. So we do want something that is clear, and we do want something that has a high degree of clarity within that. So if you got any questions, ask. Otherwise, that'll do it for chapter 4. Look for your next session just to focus on the ideas of humidity, and we will reinforce these with the labs we have in class. See you in class.